SwayamPrabha. Digital India. Educated India.
Welcome to this next lecture on vibrations of plates and shells. We were looking at the Rayleigh-Ritz method, and we started off by looking at Rayleigh's method, which involves a Rayleigh quotient. Okay, so the Rayleigh's method and Rayleigh quotient, they give us an estimate of the fundamental natural frequency. And if you manage to provide the exact mode shape, you will get exactly the fundamental frequency, whereas if you find or provide something approximate, substitute it into this Rayleigh quotient, you will get a frequency that is greater than fundamental. Okay, and the mode shapes are supposed to be admissible. Okay, what is admissible? They satisfy the geometric boundary conditions, okay, the displacement boundary conditions, or these are called the essential boundary conditions, whereas the force type are called natural. Force, moment are called natural boundary conditions. So the system has to satisfy these essential boundary conditions, or the function has to satisfy these essential boundary conditions. Such a function is called admissible. Okay. Now let us see an example here, okay, for a continuous system. So we will look at an example of a simply supported beam. Okay, so there is a beam, just simply supported. Okay, and the displacement in a mode shape, when it is vibrating freely in a mode shape, is f of x, the spatial part, and let us say the harmonic part. Okay, and from here we get w dot, the velocity, as omega times f of x cos omega t plus alpha, and from here the w dot max, the maximum value is omega f of x. Okay. Now if we compute the strain energy in the beam, okay, that is integral 0 to L E I by 2 del 2 W del x square whole squared dx. If I bring in now this function, okay, so what will it be? That is equal to integral 0 to L E I by 2 f double dash of x whole squared sine squared omega t plus alpha dx. Okay, and because it's V max, we will take the max value of this, and therefore this will be 1 at some point, so that's the max value. And then the T max, the kinetic energy max is 1/2 integral 0 to L m omega square f square dx, okay. And that is equal to m omega square by 2 integral 0 to L f square x dx. From here we can get the Rayleigh quotient, okay, the Rayleigh quotient which is omega squared is equal to integral 0 to L E I by 2 f double dash x squared dx by integral 0 to L m by 2 f square dx. By the way, this material I am taking entirely from this book, the Rayleigh Ritz method for structural analysis, I think. Okay, by S. Ilanco and Monterrubio. It's a very nice book. Okay, now that's my Rayleigh quotient. Okay, so if I plug in the exact mode shape, exact fundamental mode shape for a simply supported beam, okay, so which is what, that is f of x is equal to sine pi x by L. So if I do that, I get for the numerator integral 0 to L E I by 2 f double dash is minus pi square by L square, okay, and this is back to let's see, f double dash is minus pi square by L square sine pi x by L, that whole square dx, okay, that is equal to integral 0 to L E I by 2 pi fourth by L fourth into sine square pi x by L dx, okay. You can replace this with E I by 2 pi fourth by L fourth, okay, integral 0 to L replace sine square by 1 minus cos twice pi x by L dx, okay, and that is E I by 4 L cube pi fourth. Okay. Then the denominator part. The denominator is integral 0 to L m by 2 sine square pi x by L dx, that is equal to m L by 4. Okay. So now if I do the equation, I have omega square is equal to E I by 2 L cube pi fourth twice by m L. So this 2 goes, I get E I by m pi by L whole to the power fourth. That implies the omega natural frequency is square root of E I by m pi by L whole square. So this is known to us. First natural frequency of a simply supported beam. Okay, and that we got by substituting the exact mode shape. Okay. Now if we don't substitute the exact mode shape, okay, suppose we now, mostly you will not know, right? You have a structure, will not know what is the mode shape. So but you know the geometric boundary conditions. So approximately, suppose I choose f of x as some constant x by L 1 minus x by L. Okay. So this is admissible. This is admissible, is an admissible function. Why? Because if I have this simply supported beam, okay, then f at 0, the displacement, if I substitute 0 here, I get a 0, is 0. So the displacement condition here is satisfied. Here on the other end, if I set f of L to be 0, okay, then if I substitute x as L, and that goes to 0. So f of L is indeed 0. So this condition is also satisfied. Okay. So it is admissible. These are geometric conditions. However, there will be a moment condition that should also be 0, should be a moment condition that should also be a 0, that is not satisfied, because those are natural conditions, force conditions, force moment conditions. Okay. So this is an admissible function, but it is not the exact function. Okay. So you can now see, if I substitute this, I will get, so remember this, pi square is about less than 10 or so in the, okay. So if I substitute this function over here, I get omega, the natural frequency, as square 10.95 by L square root of E I by m. So it's about 11% higher, 11% higher, okay, than the exact. Okay. Next, so you can see that the fundamental is a lower bound, forms a lower limit, everything else will be above that number. Okay. So if we try another function, if you try another admissible function, which is what? F of x is equal to 1 minus cosine 2 pi x by L. Okay, this is admissible. Why? Because if I check f at 0, I get 1 minus 1, which is 0. Okay, if I check f at L, then I get 1 minus again 1, which is 0. Okay, so at both ends the displacement goes to 0. So it's an admissible function. Okay, if I now use this, I get an omega of 22.79 by L square, square root of E I by M. Okay, and I told you the actual value here is close to 10, about 10. So you can see how much different this is. This is about 120% higher. Okay, so if you substitute something incorrect yet admissible, then you will get a value of the natural frequency that is higher. So that's this example for a continuous system. For a continuous system, I have shown you a continuous beam as opposed to the lumped 2 degree of freedom system earlier. Okay, so again, following the same book that I mentioned earlier, we will just look at a few situations and possible admissible functions. So let's say we have a cantilever beam. Okay, so here is the wall, this is the built into the wall, and this end is free. So this end is clamped, this end is free. So what are the possible admissible functions? So at say f of x, if I consider as the admissible function, then at x equal to 0, f0 must be 0 because the displacement is 0. Same again at x equal to 0, the derivative slope must be 0. Okay, so the admissible functions are f of x is equal to x by L to the power I is equal to 2, 3, 4. Okay, so definitely x equal to 0 will be 0, and because I is 2, one derivative will still contain x, and that at 0 will be 0. So these are admissible. Okay, now the other next is a propped cantilever. So we have a cantilever, but it is just supported at the end for 0 displacement. Is x equal to 0, x equal to L. Now what do we have? the conditions are at x equal to 0, f at 0 must be 0 and f dash at 0 must be 0, and at x equal to L again f at L must be 0. So, the possible admissible functions are f of x is equal to x over L whole to the power I 1 minus x over L, I starting with 2, 3, 4, etc. Okay. Say we take I equal to 2. What we have is x square by L squared 1 minus x over L. Okay. So, definitely f of 0 will be 0. Okay. Then f dash is what? 2x by L square into 1 minus x by L plus x square by L square minus 1 by L. Definitely 0 at x equal to 0. So, these two are satisfied, and add x equal to L, this goes to 0. So, it is 0. So, this is a set of admissible functions. Okay. Next, let us say we have a pinned beam. Pinned beam. Okay, that means simply supported. So, we have a support here. It cannot support a moment. Another support here. X equal to 0, x equal to L. Then at x equal to 0, what is the condition? F 0 must be 0, and at x equal to L, what is the condition? F of L must be 0. So, what are the admissible functions? Strangely the same as before. Okay. The possible admissible functions x over L whole to the power I. Okay. This is because they need to satisfy only the geometric conditions. So, the other conditions could be different. So, you can check f0 is 0 and f at L is a 0. Okay. Alternatively, f of x can also be sine I pi x by L, and then I running from 1 to so forth. So, these are actually the exact mode shapes. Okay. They satisfy the moment condition also at the pinned ends. Okay. Then what was the number 3? The next 4. Okay. Suppose we have a restrained cantilever. So, there is a cantilever . It is restrained by a spring, let us say constant is K, and restraint is not full, is not a full restraint. Okay. It can deflect. deflection is not 0. This is x equal to 0 and this is x equal to L. So now this spring will apply a force. The spring while deflecting will apply a force up or down, whatever. But that is a force condition which is a natural boundary condition. So we don't have to worry about that. Okay. So at x equal to 0, f of 0 should be 0, okay, and x equal to 0, f dash 0 must be 0. These are the cantilever conditions, and that's all. That is all the admissible function has to satisfy. It does not have to satisfy the force condition due to the spring over here, and therefore the cantilever admissible functions hold. I think they were something like x over L to the power I running from 2, 3, etc. Okay, and let's see next. Number 5. Suppose the beam was clamped on both sides or both ends, and this one wall beam is clamped into it. This is the other wall beam is again built in or clamped. Okay. So what are the conditions? At x equal to 0, f will be 0 and f dash will be 0, and at x equal to L also f of L is 0 and f dash L is 0. Okay. So what conditions, what admissible functions hold? So here f of x equal to 1 minus cos twice I pi x by L. I is equal to 2, 3, 4, etc. Okay, so let us see for I is equal to 1, I is equal to 2, sorry. Okay, we have 1 minus cos 4 pi x by L. Okay, so f at 0 is 0, f dash at 0 is equal to 4 pi by L sine 4 pi x over L which is equal to 0. Okay. Similarly, f at L is 0. Okay. Then f dash at L is again 4 pi by L sine 4 pi which is 0. So these are set of admissible functions. Okay, and lastly for this line of this list of functions, sixth let's say is a pinned free. Okay. At x equal to L it's free, at x equal to 0 it is pinned. Okay, so what is it? What are the conditions? At x equal to 0 we have f0 equal to 0 okay, and at the other end it is free. So the admissible functions are fx is equal to x by L to the power I. Okay, I can go from 2, 3, 4. Okay. Now, in the Rayleigh method and Rayleigh quotient method, we found that the exact mode shape gives the exact fundamental frequency, natural frequency. An approximate, okay, as gives a natural frequency that is greater than omega exact. So in a way the exact mode shape minimizes, okay. So the exact admissible function or exact admissible function, yeah, minimizes the Rayleigh quotient. So what we can actually do, we can set the f of x to be a weighted sum of a set of functions, okay, whatever nice functions they may be orthogonal polynomials, okay, and then we can minimize the Rayleigh quotient. With respect to these coefficients. Then what will happen is you will find a set of AIs which when placed in this sum will give a better and better estimate of the mode shape, so that your fundamental natural frequency is better estimated. Okay. However, it turns out that along the way, okay, you can, this method provides estimates for higher natural frequencies also. Okay. When you do this, we will see you end up with a set of matrix equations where there is omega. You have to take a determinant, and based on the size of the matrices, the omega will have powers, either square power, fourth power, sixth power, and so forth, and therefore you will have omega square times three natural frequencies. It will turn out that the first, of course, is an estimate of the fundamental, whereas the others are estimates of higher natural frequencies. So this method of linearly weighting a set of functions to estimate the fundamental mode and minimizing provides estimates for higher natural frequencies also, and that method is called Rayleigh-Ritz method. Okay. The part where we estimate higher natural frequencies also. Okay. So the Rayleigh method gets extended to the Rayleigh-Ritz method when we start estimating higher natural frequencies. Okay. So what is the method now? So if I have f of x, the mode shape, and I have a summation g j phi j. Okay. I am actually running out of time, so I will start this method in the next class. Okay, we will close it here. Thank you.